Now let's see how to define the semantic rules for the kernel language instructions. So we will give the rule, the precise rule in the abstract machine for each instruction in the kernel language. So each instruction takes one execution state as input and returns one execution state as output. Remember, an execution state is a semantic stack and a memory. So the instruction is able to read the semantic stack and the memory on the input, and it can create a new semantic stack and a new memory on the output. We're going to take a look at three instructions in detail: the skip, the sequential composition, and the local. The others we'll see in less detail. You can look at them in the exercises and in the book. Let's start with the skip. Skip is the simplest instruction. It does nothing at all. So let's see how to define nothing. So the input state here has the skip on the top of the semantic stack. What it does is it simply pops this instruction off and returns the semantic stack that results. So in the diagram here, we can see here on the left, the skip is on the top, and the right is the output execution state. In the semantic stack, the skip has simply been popped. That's all it does. Let's now take a look at sequential composition. This instruction is almost as simple as skip, a little bit more complicated. So on the input semantic stack, we have one instruction that contains two parts. Look here, SA and SB, which are inside this instruction. The output here will put these two as separate instructions on the semantic stack. So if you look at the diagram, the input execution here, the input semantic stack has one instruction on the top. This is popped, and in the output we put two instructions on it, on the semantic stack. So what has happened is that the semantic stack is now one element bigger. Okay, let's now look at the local instruction. This one is interesting because it does calculations with memory and with the environment. So this will create a new variable in memory. It will also add a link to an environment. So here on the left, we have the local instruction on the top of the input semantic stack, local x in S with environment E. What it will do, it will pop this instruction. It will push S on the semantic stack for the output with an environment E, to which we have added a link with x going to little x, where little x is a variable we've added in the memory. So it extends the environment and extends the memory. So I'm not going to explain the other instructions in complete detail, but I will give you some comments on them to help you understand them. So for example, here, x equal v, the value creation assignment instruction. V can be either a number, a procedure, or a record in our kernel language. So for each of these three cases, we have to create this value in memory and then bind it to the variable. Note that when v is a procedure, you have to create its contextual environment. That's for the x equal v. For the conditional, if x, then S1 else S2, end. If x is unbound, the instruction will wait, because in fact it's neither true nor false. It could be bound to either, so we cannot do either of the two cases. So the semantic stack will not be reduced. Nothing will happen until x is bound. This is the basis of concurrent synchronization, of data flow synchronization, and we say that there is an activation condition. X is bound to a value is the condition that we need to satisfy in order for this instruction to execute. Okay, let's now talk about the case. The case is the basis of pattern matching. Notice that the case in the kernel language only has a single pattern. If you have a case statement with more patterns, you have to build them up by using the case of containing a single pattern. And the final instruction I want to say a little bit about is the procedure call. Notice this combines with the procedure definition. Procedure definition and procedure call together are extremely important and powerful concepts in the language, and so their definition in the abstract machine is very important. They're the foundation of data abstraction. So we're going to take a special look at procedures later on in this lesson and in other lessons.